I am Ashraful Islam, working as an embedded firmware developer at DevHeads, and it's been a while. We are talking on AI on microcontrollers. In our past sessions, we we talked about how we can take data to train a model for our system, and then few weeks back we did a session on running machine learning on a ESP32, and today is a hacking session about how we can run TensorFlow Lite Micro on STM32. So it's another family of microcontrollers, ARM-based microcontrollers, you can say. And yeah, in this session, we are going to demonstrate how we did it, and I did it with CMake instead of any IDE, so that I can explain you about how to port it for your microcontrollers, your specific family. Maybe you are using something else other than STM32, maybe some other ARM-based microcontrollers. Okay. So let me show you about the project a bit, and then after that we can go into demonstration. So here is our code. We will look into this after a bit, and if we want to see the workings, and let me open the serial monitor for you. As you can see, like our model is running, and it is saying a temperature is 28.30 degrees, which is pretty hot. But we trained our model to classify it as a warm, and you can see here is confidence. So it is kind of saying it is 92% confident that my room temperature is warm. Now let me reduce the temperature of my sensor. It will take a bit. It is dropping. Just wait a minute, around a minute, and we will be able to see it drop below 20. Okay, so let me stop it there, and let's wait for the temperature to become low, and we see into. So this is a blog about how to run TensorFlow Lite on TensorFlow Lite Micro on STM32. It will be published on our website maybe after a few minutes, maybe 10 minutes after this session. Here here we can see, like, we are using TensorFlow Lite and FreeRTOS also for real-time data collection. And for to use TensorFlow Lite, we have to follow two processes. One is building the TensorFlow Lite by itself as a library, and after that we can use that library into our microcontrollers. So microcontrollers project, let's see. So for building process, it is easy. We have to clone this directory, a TensorFlow Lite micros directory, from their official GitHub account, and after that we have to go their directory, the directory name we choose to clone, and after that there is a command. We have to use the make file. So it use make. So with make we can compile it as a library, but we have to provide our architectural information. For example, we are using Cortex M generic, and our target architecture is Cortex M4. And after that we are giving the name of the library. So I want to keep it microlite, so I gave it microlite. And there is another example. It is basically same as previous command, but it is using a floating point unit. So here we have to use Cortex M4 plus FP. Now it is quite variable. For example, you are not using a Cortex M4, maybe you are using a Cortex M3 microcontroller. In that case, Cortex M3 lacks a FPU, so you have to remove the FP, and you can write here Cortex M3. And for example, you want to build it for Cortex M7, then you have to write here Cortex M7. And if you want to use floating point, then you have to provide the FP. And if you don't, you don't have to. And now after it will take quite a while, because it's quite large library if we see. So it took around maybe 5 minutes to build itself. And after that, we have to include this library into our project. So here, since we are using CMake, we are including our library using CMake here. So we have to use link directories so that CMake can detect the directory, the library we are keeping in. And after that, we have to link with the library with the CMake command target link libraries, and after that library path. Now we have included we have built the library, we have included the library in our project. Now here is a thing. What TensorFlow Lite does, it takes so many dependencies from the internet. So before, if you want to, after cloning and after building it as a library, if you want to include it your project, like include directory into your project, then it will be problematic. You will see many headers are missing because your TensorFlow Lite tree is not ready yet. So TensorFlow Lite tree is basically an folder architecture or a structure which you can use your project to as header file. So for that, you need to generate the TensorFlow Lite micro tree, and for that we have to use this command Python 3, then your create TFLM tree.py, and after your desired path where you want to store this tree. So once you are done with the tree generation, so now you are ready to include it fully into your project. So here we are including the directories to our project. So we are including the third party, then flood buffers, then TFLM itself, then TensorFlow Lite itself. So it's basically according to your project. Now we are quite done with the TensorFlow Lite. TensorFlow Lite itself, building and including. Here also we are using FreeRTOS, and we are not discussing FreeRTOS part because it was done like few months before. We already discussed a lot with with about FreeRTOS, so we are not doing it here. So still, okay, let's see. Still it is not done. The temperature is yet to go down. Okay, so let me check. It will go a bit after 20 degree. We can classify it as cold, but okay, let wait. Seems that it's not going low. Why is that? Okay. So it is showing hot because of while train the model, it is we took less data for hot because for that it is predicting a bit wrong in case of the hot classification, but it is perfectly working for warm and cold. So we saw about warm, but let's wait since to it become cold. Just okay. Let it be a bit lower, and we will move to our project. Now, as for FreeRTOS part, we have done this before. Now let's see the project itself. Let's see the code, the real code here. So here we are including all the header files. So here we are some header files coming from C library itself. Then here are task, semaphore, and FreeRTOS.h. These are related to FreeRTOS. And here are all the library included necessary for the TensorFlow Lite. And these are basically our device drivers. So we are using a timer, we are using a DST sensor, we are using a GPIO library, and the clock, it is basically to set our clock speed maximum. And here we have library for UART, and here is our model. Basically, these are our own written library. Like we prefer to write everything from register level from scratch. So let's get into the explanation a bit. So here we are using semaphore. So why semaphore? It can be a question. So we are using semaphore for inner task communication because we divided it into three segments. One is for reading data, reading the temperature. Another one is processing the data and running the inference, like quantization, data quantization, and running the inference. And after that, logging the output. So we divide it into three tasks. Now, why we use semaphore? The thing is, for example, imagine a situation where our temperature is not updated yet, but due to context switching, our task switch. So it is jumped from the reading data task to processing data task. In that case, what will happen? We will process the same data multiple times because before reading the data, it changes its context. So it is basically switch the task for that. So to control that flow, so that we can make sure it will only jump to another task, not jump, it will continue the other task when the previous task is done. So to maintain the hierarchy. So for that's why we are using semaphore, and there is like two semaphore, and one is sampling done and processing done, and basically these are binary semaphore. Either it will only represent two state, since it is a binary semaphore. And here we are using an error reporter, and an error. So in TensorFlow Lite Micro, an error reporter is must needed because when you want to work with a library, and it's a really large library like TensorFlow Lite Micro, many things can happen. Suppose you are trying it for first time, and there can be some error into your code, like the way you are using the code. To get all those error in your serial monitor, so you have to use an error reporter, and that's why the error reporter here, it will report all your error. It uses an internal API called microprintf, which will print, which you have to modify according your need. Here I am redirecting that into my UART, so I can see the result on my serial monitor. And then the model. So when we are using TensorFlow Lite on a microcontroller, we have to convert it into a C array. So C or C++ array, you can say. And if we see here, we have done it. So here is a Linux tool called XXD. With this tool, you can convert your TF-like model into a C array. So here you can, I am using C++, so I am using that. So basically it's the same. The array in C++ and C, it is same kind of. So after that, we need resolver. Now, what is basically operation resolver? Now, what is operation? For example, you can say we do many operation in our real life. When we want to calculate the price of something or some product, we use addition, division, multiplication, subtraction. Then in case of programming, we use binary binary operations, kind of AND or NAND, this kind of logical operation also. So in case of operation resolver, it is kind of same, but these are only dedicated for TensorFlow Lite Micro. So the operation resolver depends on while the model while we are training the model, what operation resolver we use, and according to that we have to create the operation resolver. Here we are using two operation resolver, as you can see, at fully connected on and at softmax. So we are using these operation resolver to use to train our model, and now we need this to run the inference. Otherwise it will give us error. So it will probably give some message that the operation, the OP code is missing for this specific operations. And after that, to run our inference, we need something called Tensor Arena. So Tensor Arena is basically, you can say, an array where your TensorFlow model will run the inference. Your interpreter will run the inference on that space. So it is pre-allocated because heap allocation, dynamic allocation is like it is better to avoid in case of embedded system and when we are using really tiny device with really tiny memory. So for that, we have created an array named Tensor Arena, and with that array and model and operation resolver, we are creating an interpreter. So this interpreter is the main thing. It will run the inference. So when we will invoke the interpreter, the inference will be run, and we will get output for the input we given. And here is a function. It is declared here. The definition is like below the main function, and this is debug callback. So as I said earlier, our error reporter used microprintf function, and that microprintf function I redirected it to my UART peripheral. So and that for that to redirect it to the UART peripheral, we need a callback function we have to register this callback function as a you can see here here is our where is the function register debug callback. So this is a function comes with the TensorFlow Lite micro, and in this function you have to pass a function which takes an string character pointer. So I have created it, and after that I am just registering it here so that we can use UART for see our output data. And after that it is related to our DST sensor and a variable for store the temperature. Then these are the tasks, the declaration of task. We are going to see the definition. Sorry, we are going to see the definition a bit later. Now let's see our main function. So here we are setting the system clock speed to 180 megahertz. Is there any question, anyone? Okay, let me check. Can you make the code window full screen? Okay, let me see. Okay, no. Sorry, it is full screen, and let me zoom it. Is it okay now? Sorry, I didn't notice. Zoom a bit more. Okay. So, yeah, and now is it okay? Okay. So here we are setting our clock speed to 180 megahertz. Basically, it is the maximum speed of the microcontroller I am currently using. It is STM32F446RE. Because running inference is a heavy task, and if we use the default speed, which is 16 megahertz, then your inference will. Can you share the code? Yes, I can. After the explanation is done, I will share the GitHub repo. So no worries. So I am setting the clock speed to its maximum so that our inference can run smoothly. So it will seem like a normal instruction. It is actually really real time. There is no such delay. And after that we have to initialize our GPIO so that we can use UART, and then we have to configure our UART peripheral by itself so that we can use that also. And timer is needed. Timer is needed for basically it is needed for the DST library, because without initializing the timer, DST won't work, because DST has a certain sequence of reading data. That is, for now, that is out of the topic. You can check once I share the GitHub link. You can go into there and you can see the library code. And if there any confusion or you want to understand something, you can ask me anytime in our David's Discord server. And as I said earlier, we are registering the debug log callback so that we can see the debug log via UART. And here, as I said also earlier, that these semaphores are binary semaphores. So these will represent two states. One is given or taken. So when a certain task take places, it will take the semaphore, and when it is done, it will give the semaphore, so the other task can take the semaphore. And here we are checking certain things. So we are checking the model model version is like same to our, the trained model version is same to our current TensorFlow Lite micro version we are using here. So that is here. If it is, if it is not same, then you have to make sure that they are same. Otherwise, your inference on run, you will get an error here. Okay. And then we are registering the resolver, the operation resolver, so that our interpreter can use this resolver to run the inference. Then we are allocating the tensor. So when we are calling this interpreter dot allocate tensor function or method, it is basically a method. So our tensor is allocated. It is ready to take input, and it is ready to give. No, it is ready to take input, and after that we have to invoke so that we can take output from it. And these are basically FreeRTOS related. We are adding all of these tasks to our scheduler, so that our scheduler can switch between these tasks. So we are providing the task function name and the name of the task, and then stack size, and there are some parameters, and these are priority, and for the parameters these are null, so these are not necessary for our task. And after that we just run the scheduler and we are good to go. Now for UART, you can see here is some code. It is basically back then I was practicing driver writing, like developing driver from scratch. So for that reason, it is one of the driver I wrote when I was learning, and I am using that. And here here also I am overriding the IO putchar function, so that the C printf and the, like this function we used to write like this printf. So printf hello world, printf hello. Okay. So here it will redirect it to UART, because we have override the IO putchar. Okay. So let me keep it here and comment it out. So the printf will use UART to log data. And this is basically a very simple, override. You just have to take the IO putchar and redirect it to like an UART API, which will be able to send character by character. And after that, you are done. Now the data reading task, it is really simple. It is there is nothing much going on. So we are calling this function dst read temperature, and we are giving it the dst struct we created before, and here false. It is it basically dedicates, like if it is true, that we will get the temperature in Fahrenheit, and if it is false, we will get the temperature in Celsius. Since we are using Celsius for our model to run the inference, for that we are keeping it false, so we will get the temperature in Celsius. And after that we are logging the data, so we are like printing. Okay, so let me show you here. Let's run minicom. Okay, for some reason I don't know why my sensor is not going below 20. It should. So here you can see it is logging the temperature. It is basically from the data reading, this data reading task, doing this logging. And after that it will giving the semaphore x sampling done. So what it is saying, I am done with the sampling, or I am done with the reading. So the semaphore is ready to be taken. And after that we are taking a bit delay, otherwise it will be really fast. And if we do it really fast, maybe our sensor won't give us correct reading. So for that a delay is good. It don't have to be 1 second. It can be less than that, but for demonstration purpose I kept it at 1 second. And here going the main processing part. So we are taking the semaphore as we compare. So it is giving the semaphore x semaphore give and x sampling done. So it is giving the semaphore, and the processing task is taking the semaphore and port max delay. This is the max delay it is taking the semaphore for. And after that we are doing everything. We are declaring and defining the input, and we are taking the fast tensor from the input, and we are checking if the input is null, So if it is wrong, if we are not able to create the input, it will throw an error on our console, but it is running successfully, so there is no error. And then we have to take this scaling factor. It is basically it is an scaled value, and it is basically the temperature, and these are our mean and the standard deviation. So 21.76, these are, it is it is our mean value, and this is 6.1 this is a standard deviation. We calculated it from our model. So while training the model, we had the like whole CSV file, and from the CSV file we extracted it. You will be able to extract it for your model also, depending on the data you are taking. And here is a part. Since microcontroller has really limited memory, it is always better to keep everything small. For that, we are like we quantize the model to make it an 8-bit integer rather than a floating point number, because a floating point number will take around 32 bit. It will take 4 byte, a floating point number. So it is taking 4 times more memory. And as for the precision, if you don't need much, you can leave some precision behind, because it is you are saving 4 times more memory. So maybe you can add more data to your model. So it is like kind of give and take. You have to balance everything according to your need. So we are doing that. And to convert our quantized like the scale value into an integer, and that will be the properly quantized value. So we are dividing it with this scale value, and this is our zero point value. So, and finally we are getting our the 8-bit integer value, which we can give input to our model. So we are giving input to our model, and then we are invoking the interpreter. Basically, now we are running the inference. So the inference will run here. After the inference, after the when the inference running the inference will be finished, it will give the semaphore. Like it is giving the semaphore. Processing is done. So it takes sampling done, and it is now giving semaphore, processing done, so that our logging logging task can you know take from here. So it is taking the semaphore, processing done. Also for port max delay is basically the max time it will hold the semaphore for. And then from the interpreter, as we provide the input into the zeroth tensor of the interpreter, we also have to take output from the exact tensor. So we are taking the zeroth index, and we are storing into the output. Also we are checking is output is null or not. And when it is done, okay, so when it is done, we will get an array of 3 values. So why 3 value? Because while training the model, we take it such a way, so there will be 3 class. One is cold, one is warm, and one is hot. So for that's why it returns an array of raw prediction values, which will after that when we process, we dequantize the value, we can see like which uh, you know which class has larger prediction value. So if the value for cold is larger, that means it will be most probably cold. If the value for warm is larger, then it will be most probably warm. Today my room temperature is very high. I cannot make it lower, sorry, but let me let me wait a bit. uh, okay, so it is here you can see, if we see, there is something called confidence. So since it is hitting the lower limit of warm, so the confidence is a bit low, 68%. But if I kept it at normal room temperature, it will be it will be like 90% or more than 90% of confidence. So here, so we are dequantize dequantize the value. We are dequantize the value. So where is our logging task? Here we are dequantizing the value. Here is our scale. This is the scale value. We also extracted it from the model, and the 0 point. And here you can see prediction, a floating point array of length 3, and we are predicting the value from the output. So as I said earlier, we are going to 3 raw value for each class, since we are doing classification like cold, warm, and hot. And for the prediction, we are this is our equation. We have to multiply the scale after subtracting the value, the 0 point value from our raw output, and it will give us the prediction in percentage, and the total sum of the predictions will be 1. So, and the rest will be divided. So maybe it can be 33% of each, or it can be 40, then 30, it can be 60, then 20. uh, 1 means basically 100%, and in between 100%, which class is taking how many percentage, that we are basically seeing. And that is basically confidence. So if it is saying 55 0.55, that means 55%, you can say. And here is the class index, because we are trying to extract the maximum, the larger percentage, the value which is larger. For that, initially we are taking the first index of our prediction array is the largest, and after that, with a loop, we are comparing it, like I am comparing it with all the other fields, like second and third position also, and whichever is maximum, we will take it as a final result. So here is the class index, and level class index, basically this is our levels array. From that, if our 0th index, that means if the 0th index is larger, then we will take the 0th index, we will put it here, and this will give us cold. And if the 1th index, like the first index, is larger, then it will give us warm, and the second index, if it is larger, then it will give us hot. And this is the max probability. As I said earlier, from the 100%, the maximum value, which class holds the maximum value, will be printed. Okay. And after that also, since we are while sampling the data, we are taking a delay of 1 millisecond. For that, I am also adding 1 millisecond delay, sorry, 1 second of delay here, while like giving the output. Otherwise this value, like our terminal, will move really fast, and we won't see anything. Let me, okay. Just give me a minute. I am doing something to make it lower. Maybe I will use some ice. Just give me a minute. See, it is already switched to cold, and as it goes down, our confidence will be increased. So it is already 96% confident that it is cold. So our model is running. So if I have to zoom it, I don't know. I can zoom it here. Okay, so let me zoom it. See, I think it is now visible. So the temperature is dropped, really quite a bit, and now it is saying cold, and it is 99% sure that it is cold. So our project is running. You can see successfully. Now let's move to the code a bit, and we have almost done done with the explanation. We only have this task. It is related to FreeRTOS, because when we are assigning a stack for, if we see here, we are assigning a stack for each task. So here we are giving it 1000 byte. We are giving it 1000 byte. So if somehow our stack is overflowed, like if we are short on the space stack space, then it will jump into this callback. It is basically for that, handling the stack overflow error. It is nothing like, there is nothing much. And this was the basically project demonstration. And any question? Do you have any question there, like related to this project, or related to TensorFlow Lite, or related to FreeRTOS, or even the driver? Your driver for the DST sensor. If any of you have any question, you can share it with me in the chat or in the questions. And also, like, the blog, here is the blog on, you will, like I explained also everything here. It will be published on David's website shortly. And also I will give you, okay, so let me share the GitHub repository with you. Let me see. Okay, so I guess, yeah, this is here. Let me share the GitHub repository. So here I provided the link to the GitHub repository. Can you share the link of the code with us? Yes, I did. Okay, how to compile TensorFlow initially. So to compile initially, you have to know like for what architecture you are compiling, and what is your what is your targeted architecture family, you can say. So it is Cortex M generic. So it will use all the resources for Cortex M generic, and after that it will compile it specifically Cortex M4 family here. Since I am using a microcontroller with Cortex M4, so I used it for Cortex M4, and I used with floating point, since I have floating point. And it is your choice if you want to use the floating point. There are some Cortex M architecture like M0, M3. This doesn't have the floating point unit, so you can like in this case you can't use the FP plus FP thing. It will give you error while running the inference, maybe an hard fault. And the other thing, you can modify this family according you need. No, CMake. Initially, it is make. It is make file basically. It is make file, and it is given into the directory. So if you see the directory architecture, it is basically in TensorFlow, then Lite, then Micro, then under Tools, then Make, and you will find the make file. And if you look into a bit in the make file, you will see all the parameters it takes to compile. Like here, it is taking target architecture, and it is taking target to compile it for Cortex M4 architecture. And also also, like I will suggest, while compiling this, if we are doing it first time, you use build type debug. So if you compile it as a debug type, then you will be able to debug inside the library. For some reason, like for example, if something is happening in the inside the library, and that is giving you like hard fault or any other error, you will be jump inside the code if you compile it with the build type debug flag basically. Then you will be able to jump inside the library. Otherwise, you won't be able to jump, and like you won't be able to say exactly where you are failing and what is the error. So for the first time, it is recommended, please compile it as compile it with debug flag. And once you are done with everything, it is running fine, you can optimize it without the debug flag, and you can run it on your project. Same also, the first thing you have to remember, please make like register your debug callback, so that anything going inside the model. Let me give you an example. So what happens? Okay, so let me comment it out and debug it. Sorry, build it. So if I build it, clean, and then let me So just wait a bit, let it build, and let's see what happens. Okay, let flash. Failed. So it is not trying. Okay, so success, we are flushed, like successfully our program is closed. Okay, so see, when I will reset, it is giving a 0. Didn't find the operation for built-in operation code softmax. Failed to get registration from OP code softmax. See, you are seeing the error output. But if you don't register this callback or any other method, like you can also use ARM semi hosting, but UART is the straightforward method. So since the softmax, operation resolver is missing, it gives us that error. But if you don't register this like debug callback function, then it will be an issue. You will be like, there will be no specific cause you will be able to say, like, for this reason it is giving us error, and without that error you won't be able to find the solution. So there are two recommendations. When you are trying it for the first time, build it with the debug flag, and also make sure you have registered and callback so that you can see everything via UART, or maybe any other peripheral you prefer, like ITM terminal. So in this way, and that was the explanation. And is there any other question? Basically, to compile the library we are using make, and to include the library into our project we are using cmake. So our project is built by build using cmake and ninja, but the TensorFlow Lite micro library, it is building, we are building it using make file. Training data in previous session. Okay, so let me I will try to find the previous. Let me see any on there. Okay, so they are disconnected, like teams who manage the resources. Are you in our Discord server, David's Discord server, or should I provide? Like, this is our David's Discord server. Not yet. Okay, so let me give you the link of David's Discord server, so you can join. And we are like, for this temperature classification, we haven't read those data. We are basically take DST11 data. So we take this data sheet and trained it. So basically it will be better. It was a demonstration project, so we kept it really simple. But since if you want to train a model according to your environment, maybe here our temperature is very high, but you are from, you are close to North Pole and your temperature is really low. In that case, it won't work. So it is recommended to read your data, read your data by yourself. We have done something similar, but it wasn't actually temperature data. Rather than it was gyroscope data, accelerometer data. But you can use like either way. And if you face any issue, you can always reach us in Discord. There is a Discord channel called AJI, who is responsible for AI related stuff. You can knock us, or maybe in general dev chat. Okay. And like, any other question or confusion? So no other question. Like, anything going on here? Like, here it is going some device driver, and TensorFlow also FreeRTOS. So if there anything you are curious to know, or if there anything you don't understand, you can just ask. Uh, it can be. It depends. Basically, we are using binary, so it's switching between 0 and 1. It is not counting actually. And what it is making sure that uh, we are basically using semaphore for inner task communication, so that we can make sure the, like, at first we done with the sampling, and then it can jump into the processing, and it can jump into the logging. Yeah, semaphore can be counted. It if it is not binary, like there can be many value like 0, 1, 2, 3, because when there is a very large amount of task or large number of tasks, it can go that way. I mean, in our case, it is binary semaphore, so 0 and 1. Okay, so you can, no, actually 3. So it has 3 tasks, but we only need 2, because we have to make sure the sampling is done and processing is done, and logging will happen. After the previous 2 is done, the third one will continue as it is. So that's why we don't really need 3 semaphore. Two is enough. And binary semaphore is the simplest one to understand the semaphore. No, not RTOS doesn't require to run TensorFlow Lite, but we included it because when we are running any inference or anything else, maybe in case you want real time data, so you don't want to missing anything. Context switching is important to you. For that reason, we are using RTOS. So you can run TensorFlow Lite Micro without RTOS also. So it depends on your application, the requirements of your application, basically. Okay, so inference is basically the data processing. So for example, you give an input to your interpreter, and then then it will process the data, and it will give you the output. So the processing portion, you can call it inference. So that basically running the model is inference. uh, do you have any other question? Okay, not fun. uh, okay, so if you are interested with TensorFlow Lite, you can try. And if you face any problem in future, you can always reach us in our Discord server. And that's it for today. We are also running out of time. Let's wrap up everything here, and let's meet in the Discord server if you face any problem. And if you don't, maybe you can help other person to fix their problem. So you are always welcome to our Discord. Thank you everyone for joining the session. We should no, we should wrap up, right? Since there is no question, and like, can you do that for me, or should I end the event? Uh, okay. So thank you everyone. Have a nice day. Okay, it is not ending from my side. Sorry. There is not.